if I were to look at a graph of this, maybe I'll pull a graph up on my screen here. So here at x equals 3, there's a hole in the graph. Okay, so I can think of this as being following a nice line here, right? And everywhere except 3, I can know what's going on. All right, let's talk about limits a little bit more from a graphical perspective. Let's look at some graphs and see if we can talk about what's going on with limits and help us understand that way. Okay, so here what we're doing is we're looking at at what happens near x equals 2. Okay, so what happens as x approaches 2? Okay, and this first graph, just looking at the graph, I can see, since this is 4, it looks like the function is approaching 4 from both sides. Okay, f of x approaches 4 from both sides. Okay, so we say that the limit as x approaches 2 of this function equals 4. All right. If I look at the next graph, as my x values approach 2 from the right, as my x values are bigger, then I have a y value of 1. So f of x approaches 1 for x greater than 2, but f of x approaches negative 1 for x less than 2. Okay, so we say, well, that's a different situation. I can't say that my y values are getting closer and closer to 1 because as x gets close to 2, because that's not really true, right? That's only true if I am very careful about my x values always being bigger than 2. Okay, so we have a different way to describe this. We still want to describe this behavior. So what we're going to do, first of all, is we're going to say that the limit as x approaches 2 of this function g of x does not exist, because it's not one single number that my function is getting closer and closer to as x approaches 2. However, we have a way to still describe the behavior. We could say that if you only look at x values bigger than 2, then it's approaching 1, and that's fine. If you only look at x values smaller than 2, then it's approaching negative 1, and that's fine. So the way that we can write that is the limit as x approaches 2, and I put a little plus as a superscript here to indicate from the right. So the limit as x approaches 2 from the right of g of x is 1. Okay, and likewise, the limit as x, oops, getting sloppy here, as x approaches 2, to indicate from the left, I put a little minus here. Okay, oops, not f of x, g of x, is negative 1. Okay, if I look at this third graph, as my x values get close to 2, the y values are getting bigger and bigger. They look like they're going to infinity. Okay, so h of x is going to infinity as x gets close to 2. All right, so what we're going to do is we're going to say, well, infinity is not a number, right? The limit is a number and infinity is not, so the limit is, doesn't exist. So strictly speaking, we say that the limit as x approaches 2 of h of x does not exist. However, we can write that the limit as x approaches 2 of h of x equals infinity as long as we keep the understanding, as long as we're all, aware enough to know infinity is not a number, so that means that technically this limit doesn't exist. Okay, so we can write this with the understanding that infinity is not a number. Okay, and we're going to do that in the future. If it's headed off to infinity, we'll write that the limit equals infinity. Okay, but it's going to be important for some things to remember logically that limit doesn't exist. All right. So that gives you an idea of some limits that do and don't exist. Yeah, that's basically what we have here. All right. So here's the graph of f of x equals sine x over x. All right. What's going on with this limit? Well, when I look at the graph, I can kind of follow along with what the graph is doing, but I have to be aware that when I plug in 0, I'll have 0 over 0, and that's no good. Okay. So here, x equals 0 is not in the domain. But I can still look at the limit as x approaches 0. And as x approaches 0, it looks like my y values are approaching 1. So the limit as x approaches 0, sine x over x is equal to 1. Okay. Now, in this example, I wrote the formula for the function. And these earlier ones, I just wrote f of x or g of x. Okay. And those are interchangeable, right? When you're writing a limit, you could write the name of the function, or you could write the formula of the function. Okay, and that's fine. All right, graphs here. Here's a good one, sine 1 over x. When we look at the graph of sine of 1 over x, it looks crazy as we get close to 0. When I look at this, I'm like, I'm not really sure what's going on. Okay, and the idea is that as I get closer and closer to 0, 1 over x is going to be a bigger and bigger number, right? If I put in 1/10, right, 1 over a tenth is 10. If I put in 1/100th, 1 over 100th is 100. And since the sine function normally oscillates, as you move along, it's going to be some oscillating between -1 and 1. Okay, but as I put in numbers closer and closer to 0, it's going to be like following that oscillation off to infinity. So what ends up happening is it zigs up and down infinitely many times as I get closer and closer to 0. Okay, so there is no one number that my y value is getting close to. Okay, so the limit as x approaches 0 of sine of 1 over x does not exist. Okay, because the graph is oscillating between -1 and 1. It's not approaching a single number. Okay, so this is another way in which a limit cannot exist. Okay. Okay, so let's look at some examples. And what I want to do with this is not try and solve this algebraically. We'll do that in the next section. Right now I want to get an intuitive idea for what limits are. And so we're going to use the graph to give us an answer. Okay, so if I look at what happens at 2, as I approach from the right, I get, my y values approach 0. But as I approach 2 from the left, my y values are approaching 3. So I don't have a limit, right? So in this case, the limit as x approaches 2 of f of x does not exist. But if I look at one-sided limits, the limit as x approaches 2 from the right of f of x would be 0. and the limit as x approaches 2 from the left of f of x. As I approach from the left, I'll get a y value of 3. Okay, if I look at a point that's not this jump in the graph, then we don't have any issues, right? So if I were to look at, say, the limit as x approaches 0 of the function, when I look here at 0, there's no problems here, right? I'm approaching 1 from both sides. Okay, so this function will have a limit everywhere except at 2, and at 2 we have two one-sided limits, but they don't match up. Okay, so maybe a way to kind of summarize that, the limit as x approaches a of f of x equals L exactly, or I could say if and only if the left and right limits match. So the limit as x approaches a from the right of f of x equals L, and also the limit as x approaches a from the left of f of x equals L. Okay, so another way to think about limits, a criterion for them, the left and right sides have to match in order for the limit to exist. Okay. Before we talked about an infinite limit, and we said, well, we can write that the limit equals infinity with the understanding that the limit exists. If I look at this example, the limit as x approaches 0 from the left of f of x is negative infinity. The limit as x approaches 0 from the right of f of x is positive infinity. And these infinities don't match. So I can't even write that the limit equals infinity, right? So the limit as x approaches 0 of f of x, I have no choice but to write does not exist. Okay, we can't write that it equals infinity or negative infinity because the two sides don't match. Okay. So when I look at a graph where it's split like this, okay, here we would write that the limit as x approaches a of f of x does not exist. But if they go to the same infinity, then we write the limit as x approaches a of f of x equals infinity. Okay. All right. So that's kind of our intuitive idea of limits and how we can start computing them, looking at graphs and looking at maybe a sequence of numbers like we did at the very beginning. And then maybe next week we'll look at how do I do this algebraically? Is there a way to break this down? And there absolutely is, and that way we can get exact values.